All right, hello everyone. Come on in. Hello, hello. Hey there. Okay, so as you can see, I've finally managed to finish grading the exams. Even though I'm able to automate them to an extent, I'm not sure that it's any faster grading them through the virtual platform than like with a paper copy. So I'm still kind of working on streamlining all that. It took me a lot of time yesterday to finish up, but here we are. So I wanted to make a note there first, and thanks for showing up to all of you who are already here. So the exam in general was a lot of people that did well. You can see the distribution is kind of highly favoring the higher grades. That's a good thing. You know, typically I'd probably expect something a little closer to a bell curve, like that. But this is certainly acceptable as well. I'd like for you to be mastering the topics and capable of doing well on the exam. So there's one thing I wanted to mention. There were a few cases of people who decided that with the first problem, the BOD problem, that it was going to be a good idea for some reason to use the book. And it was very apparent to me that you used the book, those of you who did, because you were using equations that we have not covered yet, and we won't cover for another few weeks. So either you studied well in advance, or you decided to use the book or some other resource online, which essentially you signed in paper that, you know, through Moodle, that you weren't going to cheat in any way. So maybe I should have been more clear that no, I do not want you to use the book. But for those of you who did do that, I simply had no sympathy. And so if your answer involved one of those BOD specific equations, then you got no partial credit for your wrong answers there. It wasn't a big deal. I'm not personally offended. I just thought it was, I think that if that was your case, then you probably ought to rethink your priorities and your approach to learning. So just wanted to make that comment there that, you know, I'm trying to design these exams so that you have equations on the sheet. There's no reason to go look into it. I actually spend a lot of time working on creating new problems so that it's fair for everybody if somebody did try to cheat. And so if you're going to do that, it's really not helpful, you know? So I'd encourage you to rethink the way you're approaching that. So anyway, I'm not going to bother with any, you know, any academic discipline sort of thing. I just don't think that was a very professional or upright thing to do. And so the grades are, you know, for that particular problem, the grades reflect that. Okay, anyway, overall I was pretty happy. I think you guys, a lot of you will be happy. 2 of you had a perfect score. I didn't, even before I touched up any of the grading, I didn't have to touch those grades at all, so that was excellent. So congratulations for the 2 of you who got perfect 100. All right, so with that, unless there are any questions, those should be posted now to Moodle. I did that just before we began here, so you should be able to see those any minute now if you check. And if you've got any questions in that regard, I'm happy to answer them, although I might save them for after, at the end of lecture, unless you've got something right now that's pressing on your mind. Okay, so otherwise we're coming back to membrane filtration, and I was busy scurrying around trying to get ready just now. I might go and find my my Lifesaver water bottle to show you the water bottle that encases a membrane filter. We're going to have some time to solve a few problems at the end of this lecture, so I might go ahead and try to find that while you're working on a problem here in a little while. Okay, so what I want to do today is really get into the details of how to mathematically describe membranes and membrane processes. You know, we've been talking about membranes as some sort of permeable membrane, permeable flat sheet. We could imagine it kind of like a grid or a screen where there are pores that water can go through, but particles cannot. Right? So you get particles or other objects stuck on the grid. And so with that in mind, and we think about a kind of a simple membrane schematic where we just say water is coming into this chamber, some portion of it escapes through the membrane, and then some of it is rejected by the membrane, along with presumably whatever contamination that the membrane is removing. So when we talk about the solute balance, what happens to the dissolved stuff, the dirt, the little particles that are going in the water and end up concentrated in the rejection stream or the retentate stream. What we can do is we can describe the fraction that is rejected as capital R and say that the fraction rejected is equal to 1 minus the fraction that permeates through. Right, so the fraction that's rejected is, if we reject, let's say 99% rejection, that corresponds to, the fraction would be 0.99. And we can look at that in terms of the fraction that is permeating then is 1%, right? So 1% permeation. So if we were to look at 1 minus that fraction permeating 0.01, that's the fraction rejected, right? So that's all we're saying right here, but the reason we might say, we might describe it this way is because the concentration in the permeate and the concentration in the feed might be easier to measure or easier to know than the concentration in the retentate. So what we're looking at is this concentration in the feed, the concentration in the permeate, in order to know something about the concentration in the retentate. So the fraction rejected, we can get, if we know something about how dirty our water is, and we know something about how clean we need the water to get and how we've designed our operation, then we can manipulate this and say, and just use those two parameters, and then we can know something about this concentration. And keep in mind, again, we do have a mass balance here. We're not creating or destroying any amount of matter here. Okay, so that's one useful tool we have. We can also do the same type of thing but use log units and call that R log. In the case where we want to remove 99.99% of algae, think of our previous example from last time, except we'll, instead of using like a batch case where we just squeezed most of it out, we can have a flow-through system where we have a feed, a continuous feed and a continuous retentate. And then we can say the R log, in that case, we're going to call that 4, using the same type of principle we described at the beginning of the semester in terms of using that log shortcuts. So like a 4 log removal, meaning that the fraction rejected is 0.9999, that translates to 1 minus 1 over 10,000, right? That's 4 log units, 1, 2, 3, 4. 4 zeros there, 4 log units in terms of like a base 10. And so we can take the R log of that fraction, that would be the same thing as writing, or excuse me, if we take just R of 99.99% removal. If we take 1 minus that 1 over 10,000, we get 0.9999. If we take the R log, and instead of arranging it this way, we can just simply say the log of what's in the feed divided by what's in the permeate. That's going to give us our R log solution here. So the log of 10,000, because our feed is 10,000 times more concentrated than our permeate, we have 10,000 more of these dots than we do on the other side. That's our 4 log removal, where our log is 4. So it's basically the same way to describe it, and mathematically we just put it this way. It's probably intuitive. You're probably able to intuit this just based on what it means for when we describe 4 log removal in general, but you'll have this equation on your equation sheet anyway. Okay, so that's the solute balance. There's a couple of simple tools we can use there, but we also have a water balance. And before I go on, I did mention we have this just general conservation of mass. So based on the conservation of mass, we know that this concentration in the feed times the Q in the feed is going to be equal to the concentration in the retentate times the flow of the retentate plus the concentration in the permeate times the flow of the permeate. So hopefully that's obvious. We've been doing that type of thing all semester long. This is just looking at a control volume here where that box is drawn, and even though we might be separating the mass, the membrane is effectively changing it, dictating how much is in here versus how much is in here. Essentially, it's still the same in terms of the overall mass, right? So that's our conservation of mass. Okay, so is there a major difference between effectiveness and efficiency? Okay, so that depends a bit on how you define both of those terms. So it's a good question. So you might be thinking of effectiveness in terms of how effective is it at removing a given particle. And that would be kind of what we're talking about here with the solute balance. It's effective at removing 99.99% of viruses or algae or whatever. So you can have a membrane that has X amount of effectiveness at removal, but then you also are interested in considering the efficiency, which is, and a really good question here because it really leads us into the water balance, where we think about how efficient are we. We could look at it on a water balance. How much water are we getting from the system? Like how much clean water compared to all the dirty water that we produced, or the total volume, total flow of water that we're feeding into the membrane. So there's an efficiency factor there, or you could think of it in terms of an efficiency of how much energy we're spending. And generally, there is some correlation between the two, if you're defining them this way, where, to get really high effectiveness at particle removal, you likely have to use a small pore size membrane, meaning you have to apply more pressure, so it'd be less energy efficient, or perhaps you have to do more back flushing, you have to send more water in the retentate, and you have lower, on a water basis, lower efficiency that way. So there is an important distinction I would make there. Yeah. So in terms of water balance, the way we would typically describe a water recovery rate, this time I'm going to use lowercase r. I do apologize for the different r's. I try to stick with what our book and the other resources that we have available to us use. Our book doesn't do much with it. So if you're wanting to read more about this, I would point you to our online textbooks that are available. They're linked in our syllabus. And if you need specific guidance, I can pull that up for you in a little while as to where, what chapters and what books specifically to go to. So these lectures on membranes are a bit of an agglomeration of a few different texts, and so I'm trying to keep clear nomenclature here for you, but there are a few different R's involved. So lowercase r is our water recovery rate. So how much water are we getting out the clean side of the membrane during operation? So we can define this as the amount of flow in the permeate compared to how much in the feed, right? So if we have if we're recovering half of our water, then this should be 0.5 because we have 5 units of flow coming out the membrane for every 10 we're feeding to it. And so then our R would be 0.5. So in another example here, we could say that if a system treats 100 liters per minute of water, 15% of it goes to waste, R equals 85%, right? Because our recovery is going to be equal to that Q in the permeate divided by Q in the feed. And we were given that 15% of it goes to waste, so really we could define this Q permeate as QF minus Q retentate. So essentially what I did was I just manipulated our flow balance. So here, keep in mind, just like the conservation of mass, well, that also applies to our water. So we're not creating or destroying any water in the system. We always have the total amount of flow in the feed is equal to the total amount of flow combined in the retentate and the permeate. Okay, so hopefully, again, this should be intuitive once you take a look at it. And this is again a relatively simple equation just to describe some basics here. These units we don't have to have exactly at meters and seconds. This could be liters per minute or whatever. Okay, so then another term we want to talk about is the production. How much water are we producing, and how do we know how many membranes we need to get there? So that would be where we describe flux. So, and often we use the symbol J for flux, and this is what we're talking about is flux across a membrane. So if we have, just like our granular filters, we had some sort of filtration bed and water was being applied at some loading rate, for a membrane, the same thing applies. We have some flow rate of water normalized by area. So we still have Q divided by area. In this case, it's the area of a membrane. So that's written right here. And by the way, this is going to be the flow in the permeate, because when we're talking about flux, we define it as flux across the membrane, not flux meeting the membrane. So there is an important distinction here where we might be applying a lot of flow to the membrane, but some of it is just going to the side. So really when we're talking about flux, we need to be talking about flux moving across it. Of course, area here, that will be the surface area. And if you remember our discussions, that we could have like a spiral wound membrane with multiple flat sheets in here, or a tubular membrane. So some geometry we can expect to deal with in terms of solving for membrane area. But again, this, looking at it this way, it's relatively simple. And we'll take a look at a few more equations looking at how we might understand how much flux we get given some pressure that we applied. Okay, yes, actually, so there are many cylindrical membranes in practice. I did show a few. So by cylindrical, are you meaning like hollow tube, like this? These do exist. I think the flat sheet cylindrical ones are probably more common, or we have them like this, more common than just tubular. But then nowadays there's lots and lots that are those hollow fiber ones like this, all bundled up in some container. So certainly they are applied in each way. My impression is that a simple tubular one, it's not particularly high surface area, so it would probably be, those would probably be used more often for a microfiltration rather than ultra or nanofiltration, and perhaps for smaller cases or laboratory scale studies, things like that. In reality, a lot of laboratory scale studies are legitimately a flat sheet, just sandwiched in some sort of a chamber for easy control, easy access, all that. Okay, so here's an example. And again, as always, thank you for the questions. I do appreciate that. And I believe the other students appreciate it as well. So maybe they can show some participation and thank you also. Okay, so here's a problem. And this is from one of the textbooks, chapter 12 of that textbook, not ours. Ours doesn't give membranes quite enough time. So we're going to compare an outside in and an inside out flow regime. So we have a Dow FilmTech SFX 2860 membrane module. And this membrane module contains 5,760 fibers. Each of those fibers are 1.87 meters long with an outside diameter of 1.3 millimeters and an inside diameter of 0.7 millimeters. And so we're asked to calculate the water production from one module if the flux is 75 liters per square meter. And we're instructed to do this in the cases that the flow direction is A, in outside in, and B, inside out. Well, it's 1 and 2 here. And then it asks you to compare the two answers. So let me remind you what this is talking about. So these are long fibers that have some length. And if you were to take a close-up look at just one fiber here and then kind of look at the edge, what you're going to end up seeing is a fiber that has essentially two diameters, right? So we have something like that, where the membrane material, the supporting layer, is all in there, and depending on whether we're operating on the inside out or outside in, that's dictated. That will dictate which surface of this cylinder is used as effectively the separation layer. So either we're mapping the geometry to find the surface area here in case 1, right? Or we're going to do it along the outside for case 2. I'm just cutting it in half just to kind of delineate the two different versions, but it would go all the way around in either case. I just drew it in half just to demonstrate the difference there. Okay, so I'm going to give you a couple minutes to look at that. In the meantime, I'm going to go take a look around to see if I can find this Lifesaver bottle. I'd like to show it. I might not even have it here, so we'll have to see. So take a few minutes, go ahead and do this. I'll be back shortly. Since I just moved into this house recently, I'm not quite sure where everything is, but we'll give it a try. So I'll be right back. Okay, I couldn't find the membrane system, so I will try to find that later. I think I might have left it at on campus actually. Okay, so what you're solving for, that's a good question. So it says calculate the water production. That's not very clear, but yes, the overall flow rate is what I would consider that's talking about. So water production, yeah, it's a very generic term, but it's if we have some flux and a certain amount of membrane surface area, what's that production? That is going to be that QP. Okay, so I'll go ahead and start working through this with you. If you want to solve on your own, this would be a good time to go ahead and pause. All right, so we have a length of the membrane, 1.87 meters. We have diameter, an outer diameter of 1.3. Excuse me. 1.3 millimeters. Okay, so what would be the time unit if it's not given? Well, yeah, it's right here. Kind of looks funny with those units there. Okay, so then the inner diameter is 0.7 millimeters. Okay, so then we have two diameters to use. In version 1, we're going to use the outer diameter because we're doing outside in. So really that geometry, understanding what's happening here is going to be the important part. So what I'm going to do is find the surface area of one fiber, and then we need to take that and consider how many fibers total we have in one unit, because we're talking about one module here. So the surface area for one membrane fiber is going to be the surface area of a cylinder, which is the length times the circumference. So which is 2 pi r, right? Pi times diameter. So the area, one membrane, the outer diameter, this is going to be 1.87 times 3.14 times that outer diameter, 0.0013. I went ahead and converted that to meters because we have this one in meters. All right, so let's do that calculation. Let's say area of the membrane OD. Okay, so that should be the area in square meters. Then we need to know the area for a module. And so we're going to take this number and multiply that by the number of fibers per module, which was 5,760. Also in square meters. Okay, so we've got that. Next, what we're going to want to do is take a look at, so this was, let's say, 0.0157, 152. So the area of a module is 87, but really effectively 88 meters squared. Okay, so somebody got a different area for the membrane for, did you do one fiber, 2 pi r as your circumference? That's correct, right? I'm not having a brain fart. What did you do differently? I'm going to go ahead and start working on, continue working on the problem, but let me know if you see something that's different. So then we want our flow rate. That's going to be equal to essentially the, our flux is flow rate over the area. So our flow rate then is going to be the flux times our area. And that's why we're solving for the area of the module. Okay, so you got 0.0078. So that was for one fiber, I'm assuming. Did I do something wrong? Oh, I did, yes. I should not have that too because we're working with diameter, not the radius. There we go. Okay, so that should be hopefully that should hopefully fix the problem. So then we should update this here. So it should be half that, 44. Yeah, you could certainly find the QP for one fiber and then multiply. That multiplication doesn't have to happen on the front end. That could be either place. So this one was half that. Okay, yeah, so that's certainly fine either way. But once we get the this going, then we have 75 liters per square meter times essentially 44 square meters. And what we double check, and this is per hour, what we double check is that the units are going to cancel properly. It looks like we do not have to convert our liters. We can give an answer in liters and that will be acceptable because these square meters will cancel here. Although, as you know, we could do that conversion if we needed to. Okay, so then from here, we'll say QP equals this guy times 75. That'll be liters per hour. And that's our answer. Okay. And we'll just go ahead and round up to that for liters per hour. Okay, so then we'll repeat the same process. But here we're using the diameter of 0.0007, or that 0.7 millimeters. So what we can do is we'll just take put down here. This time we're going to do the inner diameter, label it that way, and we're just going to change our diameter. Okay, so then from there, the same process should be applying, and all of our calculations then should be in place, and the area of one membrane module with 5,000 of those fibers should be 1,776, should yield that much liters per hour. So quite a bit different. If we take a look at these two, and it did ask us to compare them. So when we solve this, we get QP equals 1,776.5 liters per hour. So comparing those two, there's a variety of ways you can do that. Just simply looking at them, compare how much more does one give compared to the other. So let's just say one divided by the other. So the outer diameter gives us almost 2 times as much flow. Is what this calculation shows us. We could also look at the inverse and say, okay, well, that one's almost half of the flow of the other. So just for one module here, that difference of what, 0.6 millimeters is making a rather large impact. So when designing these membranes, that's definitely something to keep in mind there. Okay, so hopefully that was helpful. That's just a simple geometry problem to take a look at how that, how we might analyze a system based on, on the premise of how much surface area does it have and is usable. So on the pressure side of things, we want to consider that driving force, that pressure, and how that relates to how much flux we get. So our driving force is essentially that transmembrane pressure, that pressure that's being applied. So we have, if we have some membrane, then we can describe the delta P as how much pressure is in that feed being applied to it versus how much pressure is in the permeate. Now, in some systems, we might have multiple membranes one after another. That is certainly possible, especially if we have a system where we want a membrane that is a membrane system that is progressively finer pore sizes. We would want to protect the very delicate, tiny pore size membranes by putting first like a microfiltration, then an ultrafiltration to remove all the particles that might damage that tiny membrane, the tiny pores of that membrane. So, so the way we define that driving force is that pressure difference, and there might be more than just atmospheric pressure on that other side if we have something like a series of pipes. That's not necessarily the case, but sometimes it is. So then what we want to do is look at that pressure across the membrane. And what we'll do is we'll look at this in pascals. So the PF is the feed pressure, P here is permeate pressure. And then we can relate this to flux by saying that our flux is going to be equal to this pressure divided by something that tells us how difficult it is to push water through. So this portion here, this is the total membrane resistance times the viscosity of water, dynamic viscosity of water. So this is like how much pressure is being applied divided by the difficulty of water, the difficulty water has for passing through, which is sort of like a drag, or yeah, it's sort of like that drag force. So total resistance is measured in per meter. And if you think about it, what we're talking about is a value that describes resistance for water going through a meter of this stuff. So how much resistance in a meter of membrane? It's going to be a lot. Normally we're dealing with tiny membranes, very thin membranes. So when we look at this number on a per meter basis, it tends to be very large. It'll depend on the type of membrane, of course, but something like 10 to the 12th per meter. And that, it kind of makes sense when you end up thinking about it. We're normally using very small, very thin membranes, so the fact that we're using meters just makes it compatible with our pressure units and all of that, but we don't have a full meter of membrane, so this unit is kind of describing per 1 meter of it. That's going to be a large number. Okay, you're familiar with the dynamic viscosity of water. The only thing I'll say here is remember, when you're using the lookup table that I provide on the exams and that our book has, remember that this is something like 1.139 or whatever, but it also has that times 10 to the minus 3 in the units. So make sure you're writing out the units and you're not missing that times 10 to the minus 3. There was certainly some examples on the exam where some of you forgot to do that. Okay, so just a few pictures here to kind of visualize where this resistance is coming from. If you imagine pushing some liquid through these membranes, you can certainly see that in some areas of these membranes, it looks like water can freely flow through these more open channels. And this is a good view of what you'd expect to be a supporting layer. And then either this surface or maybe this surface is the separation layer. And you have small pores in the separation layer that are leading to these bigger channels, is the idea. So then what you want is a very thin layer, thin separation layer, that all of your resistance is being applied by that thin layer. You don't want more resistance than you have to have. So there's an important distinction here of the separation layer versus the support layer. And here's another good example where you can kind of see this delineation here where it gets really fine versus the much larger pores. So the much larger pores, they're going to have a lot less resistance to the point where it's not even really a factor to the total resistance. That total resistance is going to be captured by what's happening here. Now, in addition, and again, another good example right here where you can see this support layer and it transitions into a separation layer here. Okay, so in addition to this, the membrane itself, this is all innate membrane resistance that we're talking about. You could also have fouling layers. So if this was our membrane here, this portion over here, then we start getting particles and junks situated on top of the membrane as we're doing our filtration. You can imagine those as these little spheres here. And what happens is if you get enough of that, then you're eventually pushing water through this fouling cake that itself is acting like a filter. So when you accumulate enough junk, then you have an increased resistance because you're effectively adding more membrane. And it's more depth as well as potentially being finer pores for water to travel through that network of particles, right? So it's not only traveling through the membrane itself, but also this cake layer. So when we talk about membrane resistance, we end up talking about the fouling layer as well as and the membrane fouling in general, as well as the membrane resistance itself. So when I say fouling, I'm talking like a foulant. The membrane is fouled. I think I think that's what you're referring to. So we can describe the pressure requirement in terms of how much stuff is getting onto the surface of the membrane. So if we have a membrane here with a separation layer and kind of a network of pores for the supporting layer, what we can consider is what happens when we foul the membrane. We use some green particles, green junk, getting on here. So we can consider 3 different types of resistance. And by the way, Reese, let me know if I didn't answer your question or if it's not here. So we can consider 3 subcomponents of total resistance of a membrane, and that would be the membrane itself, meaning the pore size of the membrane, that would be Rm. That's just innate what the membrane is up to. Then we can have what we call a foulant resistance, and I'm going to show that one in blue here. The foulant is generally particles and foulants that occur within the membrane and all around it. There's a better schematic here in a moment. But this is going to be particles that just get stuck along the way, at the surface, inside, just fouling it generally. So what I'll say is RF here. Now, if we let the membrane operate for long enough, we do end up getting a cake layer formed, and we end up with this cake filtration. So this would be our RC here in that color. Whereas if we have a clean membrane, then it's just resistance due to the membrane itself. Or we can have some contribution of fouling that happens generally inside of it. So all of this is to say that we can describe the reasons that it gets harder to push water through a membrane based on the fouling mathematically. And we do that with a simple equation saying that the flux is related to the amount of pressure we're putting divided by this resistance term. And the total resistance is just a sum of these different resistances. Now, you could think about the membrane resistance itself. I mentioned this earlier, but you could say that this supporting layer here does contribute some resistance. But if it's a small amount of resistance, if it's designed well and it's not very, it's very porous, it's not very tightly bound, then it's going to be like a decimal place, right? If we have 10, well, let's say if our membrane resistance is 8 times 10 to the 14th resistance, well, chances are good that this the separation layer is giving most of that. But if you were to separate it out and decide to say, okay, well, what is the resistance of the supporting layer? That's probably going to be like a 0.000001, right? It's going to be so insignificant that, or we want it to be, that hopefully it doesn't matter in terms of our total operation, right? So if we had 8 times 10 to the 14th as our total, it's going to be some summation of the resistance provided by the membrane itself, plus any cake layer filtration that we're going with, plus whatever resistance is added by that foulant, just the generic fouling. So all of this to say that the membrane cleaning is really important, because when we're operating a clean membrane, we know the specs, we know exactly how it's going to operate, and I think we saw last time the amount of water we get out of a membrane drops pretty quickly compared to for a membrane that's becoming dirty compared to a nice clean membrane. So here's another example of the fouling types, and more often than not, it's a combination. Now, there is a chance we can get complete plugging of pores where a particle just sticks right in that hole and it's the exactly right size and it doesn't come out. This is not, to my knowledge, this is not a hugely common problem, and certainly something that backwashing would easily help. The standard blocking would be kind of that general fouling that I was talking about, and then if you let that go for a long time, then you get this intermediate fouling where you're getting a little bit of a cake layer and the stuff inside here. And you can see this is constricting the pore volumes, right, and the pore sizes. So that's going to be, you can see visually how that's restricting the flow. And then eventually you usually get to cake filtration, which some membranes are actually operated with that in mind, to create a cake and let that cake do some of the work. So sometimes that might be a little bit useful, and in a lot of ways it's simply inevitable. So with that in mind, we can take a look at one more term called permeability. And this is one more way we can associate the pressure and flux, just based on a different parameter. So if we define permeability as LP, we're going to say that the permeability is equal to the flux divided by the pressure. The units here come out to be meters squared times second per kilogram. And so this is essentially, again, if we kind of take a look at these pictures, how permeable the membrane is. It's a measure of how much water goes through given some pressure. This is similar to Darcy's law, the permeability of a soil, something like that. And it gives us some, another metric, or perhaps a way to estimate, if we know something about the geometry of the pores that we have in mind, we might be able to predict the permeability based on that geometry, and then take that and say, well, we can predict the flux, we can predict the pressure required, or maybe we can know something about how much fouling will restrict that flow. Okay, so another example problem here, and I think this will be the last one for today. Yeah, we have a few slides to do parts of it. Okay, so we have operators of a small groundwater cleanup decide to implement a cross-flow microfiltration membrane unit as a pre-treatment step to ensure that influent groundwater into the treatment setup does not contain large particles that may clog the other stuff. The system must treat 200 liters per hour. It utilizes a membrane with a pore size of 2 micrometers, and it must recover at least 95% of the water. The influent water contains 30 milligrams per liter of particles, and the membrane rejects 85% of particles. Okay, so a lot of information given there. Part A says, label the feed, permeate, and retentate streams on the diagram below. Yes, I am sorry. Certainly can do that. And thank you. When I read from my second monitor, like I can see the same version of what's on the screen with the smaller plus the text on my left monitor, but when I'm reading, it's just a little bigger over here, so I didn't notice it first, and I do apologize. Okay, so a bunch of information, and the first part A, was asking us to label the feed, retentate, feed, permeate, and retentate streams on that diagram. Then we go on to look at the concentration of particles in the permeate, the concentration of the particles in the retentate, and then finally, if the membrane is rated for some flux, what is the total membrane area required to meet the flow demands? Okay, so that's kind of the big picture. I'll go ahead and label these with you. We don't need 4 spots, but I went ahead and put them on there to remind you. Obviously, this is the feed. To remind you that anything that crosses this boundary is what we consider the permeate. So anything being collected on this side of the membrane, that's going to be our key permeate. So you can describe it with either C or D here. And then of course, this is our Q retentate. Okay, so that's all that part was. So then part B says, what is the concentration of the particles in the permeate stream? So go ahead and take a moment, consider how you would go about that, and we'll set up to solve this. I'm just going to go ahead and write some of these variables into Excel so that we'll have those all set and ready. Yes. Yeah, so I'll leave it on this page until we start solving, and then I'll do the solutions on the following slides. No problem. Okay, so I'm going to go ahead and move forward. Again, you're always welcome to pause if you like. Okay, so first of all, I just went ahead and put in some numbers here to Excel. I put the flow rate that we're required to treat, and what I would say is this is, based on the way it's worded, it is a little ambiguous, but I would expect that what we are talking about is how much feed the membrane is designed to treat, given the rest of the parameters. And the reason I'm saying that is because we are treating contaminated water, and usually when we're treating a contaminated water, we are looking at what flow of water do we need to treat in order to contain our contamination properly. If we were producing water, I would try to rephrase this better if I were to write it myself, so that, in fact, I probably did write this myself, so I would try to revise that to make sure that we are looking at the amount of water that is produced and usable. But in this case, it says it must, this groundwater cleanup must take care of this amount. So we're going to go with Q feed for that. And I'm going to try to be a little clearer. I always try to say more clear, but technically it's supposed to be clearer. Anyway, I'm going to try to be clear about that on any exams or homeworks. Okay, so I've just put in some data here. We have the water recovery rate needed to be 0.95. The rejection rate needed to be 85% or 0.85. We know the concentration in the feed, and for the last problem, we are given a flux to work with. Okay, so we'll come back to this in a moment. So part B is asking, what is the concentration of particles in the permeate? And again, you can just describe a simple system here to visualize something like that. Okay, so what's the concentration of particles in the permeate stream? We're looking for that CP. We need to know that. Now, before I, excuse me, before I really get into, I think the fish cam's just gonna have to go away for right now. Before I get into the setting up the exact equation to find my solution in the first place, or what I'd like to do is go ahead and take a look at the flow rates. Flow rates, usually they're pretty easy to find and identify given the problem parameters. So we know we're taking the Q feed to be 200 liters per hour. And then we know something, given that we know that we have to recover some amount of the water, that really QP, the amount of flow in the permeate, should be at minimum 0.95 times QF. So that should tell us that our Q permeate should be 190. If I'm doing that right in my head, which I believe I am, that should be our number there. So that should be 190 liters per hour, which is 95% of the flow. That means that our QR will simply be 200 minus 190, giving us 10 liters per hour. Okay, so that's kind of one of the first things I would do, just to put that out there, kind of in line with just drawing my situation and identifying stuff. And maybe what I ought to do is go ahead and put that into Excel as well. So here, let's go ahead and write those things out that I just solved. So QF we already had, QP, this is got 190 liters per hour. QR then is 10 liters per hour. Okay, so then to find our concentration in the permeate, well, turns out I don't think we really had to do what I just did first, but I went ahead and got that out of the way. The reason I say that is because we know what's in the feed, right? The CF is 30 milligrams per liter of particles. And we are also given this rejection rate. So we're rejecting 85% of particles. So if we remember the R, that's going to be equal to, we can equate that to the amount of particles remaining. So the particles rejected would be 1 minus particles remaining divided by what we started with. We could also say this is CR divided by CF, right? Should be the same thing. So we can solve this for CP rather easily. And so we can say 0.85 equals 1 minus CP that we're looking for divided by that 30 milligrams per liter. Okay, so what we want to do then, we'll go ahead and add this guy to both sides. CP over 30 equal to 1 minus 0.85, leaves us with 0.15. Then we can have CP equals 30 times 1.5, excuse me, 0.15, and that will be our answer. I'll go ahead and put 1 minus the R here. And we should consider for a moment that if it's rejecting 85%, that means we should have 15% left over, and that math should work out nicely if we consider that our, we could have done this in our head basically, that the 15% of 30 is 4.5. Okay, so that would be our answer for the concentration in the feed, in the permeate here. Okay, so not too confusing there. Yep, that sounds good. So we'll talk about that in a couple minutes then. Okay, so this is the way we can use that R to get that answer. So part C asks us what is the concentration of particles in the retentate stream. So again, we're looking at our system. We have a membrane, got the feed, got the retentate, and the permeate. Now we're interested in this portion here. So, and I'd like to draw that a little better. QR and CR. Q feed, C feed, and Q permeate, C permeate. Okay, so here, what we're looking for in part C is concentration in the retentate, and I mentioned just a moment ago that we could also make this relationship where we have CR divided by CF is equal to R. So it should be equal to R times CF. No, wait, I did that. That's not correct. I don't think that's correct. Hang on. Let's just do this the proper and easy way and say this is going to be, what we can do is just say that CR times QR is going to be equal to what's coming in the feed, Q feed, C feed, minus the QP CP. Now there is an algebraic way to relate the, like I was trying to do a moment ago, but I'm not going to bother thinking that through on the fly because it's not making sense at the moment. And I'd like to finish the example and get to questions and not make mistakes. So we're going to do it this way. Certainly there's going to be another way. So what we want to do is identify CR then. So we have QF, CF minus QP, CP, all that divided by QR. Okay, yeah, and maybe I am correct if I do it that way. Yeah, might just be second guessing myself and not wanting to be wrong on camera. Oh no. Okay, so we're going to say that our CR here then, we'll go ahead and put in these numbers and say this is going to be QF times the concentration in the feed minus the QP times the concentration in the permeate, which we just solved, all of that divided by the concentration in the retentate. So the concentration in the retentate, and I'll explain in just a second, Reese, why I was wrong, but this is correct here. I think it'll make sense for you. Yeah, you probably already see it. Okay, so back to the PowerPoint. You know, with these stylus pens, you actually do need to use the right way. Yeah, so the less water is why this becomes such a big number. So 514.5 milligrams per liter. Now, one thing to note here, we have, whenever we are using a filter to reject stuff, and some of the water is going through, we should, if we're rejecting anything more than 0%, then we should have a concentrating effect, so that we should be able to double check our answer that whatever our answer is in the retentate should be larger than what we started with. Which is why it was not making sense to just multiply by that ratio. I think maybe if we divide by 1 minus R, then it works out. But yeah, this is the safe and easy way to do it without worrying about that. Okay, so part D, if the membrane is rated for a flux of 25 liters per square meter per hour, what total membrane area is required to meet the flow demands? As I said at the beginning, there's kind of two ways to interpret this. 200 liters per hour is what I said the Q feed would be. You could potentially say that's going to be the Q permeate. That would change the solution a little bit. I'm going with this being the Q feed, and I'm also telling you I'm going to try to take special care to make this more clear on future problems. But with this assumption, that means our Q permeate, we already solved for, was 190 liters per hour. And when we talk about flux, we're talking about flux across the membrane, so we actually have to use our Q permeate when we solve this problem. Okay, so we need a QP at 190 liters per hour. So we can say our flux is going to be equal to our flow rate divided by the area of the membrane. So that means our area of the membrane is going to be the flow divided by our flux. And that should give us our area. So when we do that, it should be equal to that flux we were given divided by, or excuse me, that should be the flow. Should be the flow of the permeate divided by the flux that we're given. And let's double check here. We have liters and liters, square meters, and hours and hours. Okay, so that should be okay. So that gives us 7.6, and we're left with square meters. Because that was going to be, let's go ahead and write this out, 190 liters per hour divided by 25 liters per hour per square meter. Yeah, so all those units should cancel out nicely, and we'll get meters squared on top. Oh, well, I went ahead and did that. Okay. All right, so I know, Reese, you had a different way of doing, I think, part A. Happy to talk about that. I think that's a common issue, if I'm remembering these numbers correctly, from past years of doing this problem as a homework or exam problem. So I'm going to come back to part A, unless there are any other questions, and we can talk about how that did. I meant part B. Yeah, part B here. So any questions or issues? It looks like maybe the stream dropped for a moment a little while ago. It said welcome to the chat room at some point. So sorry about that. If there are no questions or issues, I will see you next time. I will, like I said at the beginning, the exam grades are up, and I do hope to get you a homework assignment and some of the Moodle quizzes going soon. Okay, so Reese, let me know if there's some question you had here, trying a different way, or anybody else if you've got a question. Okay, you took 200 liter times 300 milligrams per liter, so the total number of particles in the feed, then multiplied by 0.15 to get the number of milligrams of particles in the permeate. Then you did 0.95 times 200 to get 190 liters and did 90 milligrams per 190 liters. Okay, so that, you're doing it essentially as if you're doing one batch of 200 liters and 190 of that gets through. And it makes sense why you would do that, because that's what I showed you with the batch case where we filtered a set amount of water. That makes sense. Yeah, so it makes sense that you would approach it that way. And in fact, what I'm realizing is perhaps that was a misleading way to instruct you on accident here, of course. Yeah, so you disregarded time, and I think that comes down to the difference that we were talking about last time when we had a batch and some of it was not filtered, right? We started here and then it went down and we got to here. And what I said was, well, you don't want to treat the whole batch as if it was filtered. You only pushed so much through. But in the case of a flow-through system, I think the math works out differently, because everything that hits the membrane met the membrane at some point. So then the flow, in a flow-through system, all of the water that reaches, let's do this. All of the water that comes out as a permeate did contact the membrane. And so I think that's going to be the difference here in terms of why we have, that difference that you're noting there, relating it in this fashion for a batch compared to the equation we're given for this continuous feed problem. And so not just that you're disregarding time, because it's fair to say if you operate it for 1 hour, you can look at it that way. However, I think that way of looking at it is taking this to be 190 that permeated through and the remaining to be 10, as if that 10 never reached the membrane, which is not correct in the system where we have the continuous flow, which is why we need to use this mathematical setup. Does that make sense? I think that's why there's a difference there. No, that's great. And to be honest, I have given this problem in the past with these numbers, and a lot of people would report 4.74 when the answer was 4.5, and I was always trying to figure out why exactly that was. So this is kind of helping me understand that approach better. So yeah, and it's a pretty good estimation. It's interesting. Okay, well, I hope that helps whoever else was hanging around. Any last questions before I go? Yeah, and thank you as well. All right, so I'll see you guys on Thursday then.